So before, what's going to happen is we've got one last, this Thursday lecture, I've always thought about covering this brand new material. Because I'm leaving, the motivation to push boundaries is kind of low. I know. So what's going to happen is I'm going to do this one problem that I really want to do, and then we're going to talk about the last type of new material. And then if whatever we can't get done with that, we'll finish Thursday. And if we get done with all of that today, Thursday, Friday tutorial, new problem set out on Thursday, due next Tuesday, it will be small. Just a few small problems. But Thursday's lecture will probably be either tutorial or review session. Friday will be a tutorial or review session. If only 2 people show up, I won't do it. So hopefully we'll get like I need like a half dozen people for me to feel it's worthwhile. And then the following week, Tuesday lecture, and Wednesday afternoon we'll have a review session. So there's basically going to be a whole week, almost 9 days. Okay. Someone asked about an evil problem. You want evil? Let's get evil. So we have a signpost that can pivot, but it's not. We have a string holding it up. Now some of you may want dimensions. So y equals 1 meter. x1 equals 2 meters. x2 equals 1 meter. The bar is massless, and the string has a mass of 40 grams. And already we can start telling that this is in dangerous territory. Hanging at the end of the string is a big hunk of rebellium. The rebellium has a density of 2,500 kilograms per cubic meter. It is sitting in a vat of water. I'm not a monster. The density of water is 1,000 kilograms per cubic meter. So, the base question is simple. What is the volume of the mass that's submerged in that water if the third harmonic of the string is 1,200 hertz? It's one of my favorite problems. Now, when you sit here, this is one of those problems where it freaks everybody out because it just seems so complex. This problem here, basically how I'm going to do it, is a lot like me deciding, like, you know, like biology classes, they'll bring in animals and stuff, I don't know what they do, but if they brought in, say they had, we're going to bring in a velociraptor, but it's going to be in a cage, so you can look at it. Now, if it got out of the cage, we're doomed. But this is a problem that I'm going to work through. I'm going to show you all the parts. And if you take this problem and embrace it and understand it, and get rid of all your anxiety about it, it should be fun. So as far as I can tell, there are 3 subjects that I really need to know about in order to better understand this problem. What are those 3 subjects? Give me one. Buoyancy. You got to know how that buoyancy affects the tension of the string that's hanging at the end of the pole. So we got to think about buoyant force, we got to think about gravity force, we got to think about tension, we got to think about all sorts of things. What's the next subject? Torque bar. This thing's a torque bar. We got a string pulling up the post. We got a mass at the end with the tension pulling down. We know for a fact that it's, and one of the questions that you could ask is, well, what is this thing doing aside from the vibration? Nothing else. So the bar is not moving up or down, and it's not rotating. So therefore, it is in blank and blank equilibrium. Rotational and translational. Rotational is going to be the more important of the two. The last part is what? Oscillation, sound, plucking a string. So we have to have all this information, and we're going to piece together all of this in order to come up with our answer. We can do this in a wide variety of ways, but let's just talk about the general subject matter. The first thing that I deal with is I've got a mass, I've got a frequency. Let's talk about the harmonics. F equals NV over 2L. Well, N is the harmonic. We have that. L is the length. So we can do N over 2 x1 squared plus y squared, because L is equal to x1 squared plus y squared. And then there's V. Yes, thank you. And then there's V. V is the velocity of the waves in the string. What 2 quantities am I dealing with to determine the velocity of the waves in the string? Think about when we plot the car string. What two quantities help you determine the velocity of waves in the string? Remember how I tightened it? What does that change? Tension. Tension and what kind of density? Linear density. Fat strings versus thin strings. Low frequency strings versus high strings. High tension strings, high frequency. Low tension strings, low frequency. So the velocity is tension over rho L, the linear mass density. I could write just rho, or actually what I've been teaching you guys is to use lambda. So this particular tension here is the tension pulling up on the bar. The linear mass density, lambda, is the mass over this length. So V is equal to TL over M. 1 over lambda flips this and I get L over M. This mass is that. And L again is this. And then you get that. So this becomes that. So frequency is n divided by x1 squared plus y1 squared square root. Tension times this length divided by the mass. So we did all the substitutions. Now, one of the things that I would expect the 211 students to do is keep everything in alphabet soup mode, but I can hear the popping of brains in the room. So what I'm gonna do is I'm gonna plug in the numbers and give you a number times some value of tension. So this gives you F equals 3 divided by 2 squared plus 1 squared square root of T two squared plus 1 squared square root over 0.04 kilograms. So what I did is I plugged in all the numbers. Sometimes when you're manipulating equations, yes, it is nice to occasionally just plug in numbers and simplify it. And you also notice this is one problem that's going to take like an hour to do, or 45 minutes to an hour. But when you look at this particular problem, it is not one problem. It's like a dozen problems all in one big thing. You guys are senior level Physics 213 students. We are now being able to push the boundaries and get you guys to start thinking about problem solving on a different level. Because I can hear in your heads, half the class is going, I don't know what's going on, and the other half is, I'm barely holding on, which means we almost have dogs and cats living together, mass hysteria. Yes. I can't hear you. Where does the 3 come from? So here, I'm dealing with 3 divided by 2 times the square root of 5. And when you're doing this plug and chug thing, which I don't normally do, I'll extend the numbers just a bit. This is the square root of 5. This is 0.04. So this is 55.902, or actually 9017 times t. So we got a lot of numbers going on with this. And what I'm going to do is I'm going to square it . Because what I want to do is I want to figure out this number as a function of t, not square root of t. So f squared is equal to ooh, that's kind of interesting. 0.45000 times 55.90 t and I get f squared is equal to 25.1550 t. And tension, the tension in the string, oh actually, why? Begs the question, why did I not plug in f squared? So with all this information that I have, I effectively have the length of the string, I have the mass, I have the density, I have the frequency, I have the harmonic. I can get the tension in the string easily. So 1200 squared divided by 25.155. And I get 57.245 newtons. Now, I will admit this. I'm rounding. Now, granted, my sig figs are out to 5 or 6 places. So the bit rot is going to be pretty small, but it will eventually, with time, build up. For the 211 students, if I were teaching them, I would force them to take the equations to their conclusion and have just one big equation and solve it that way. But what we've done is, from this problem, there's one part that we can easily get. We can get that. If I said, he's doing a great job of blocking your head because you're looking at me. If I simply ask, given this string with that frequency, harmonic, mass, and length, give me the tension, you could go, oh, that's no big deal. You just solve it that way and just crank it out. It's not a big deal. The next part is the torque bar problem. The way that this thing is set up have an angle theta, distance x1, distance x2, some tension pulling down, and I'll use actually, I'll call that T1. T1 is pulling up and to the left. T2 is pulling down. The bar is not rotating. I have x1 and y. That angle theta is inverse tan of y over x, which means this is inverse tan of 1/2, which means that my theta is 26.565 degrees. Now this particular T1 is pulling to the left, which is Tx, and pulling up, which is Ty. If that is theta, then sine of theta is Ty over T1. Or T1, or I'm sorry, Ty is equal to T1 sine theta. So the tension in the Y is T1 57245 times the sine of 26.565 degrees. And the tension in the Y is 25,601 newtons. That's the tension in the Y direction. This problem is a variant of, occasionally I've given you the problem of, given a mass hanging at the end of a rod, what's the tension in the string? Now the problem is, given the tension in the string, what's the mass at the end of the rod? We're working in the opposite direction. We know it's not rotating, so sum of the torques is equal to 0. There are two forces or two torques. T1y x1, T2 x1 plus x2. Now T1y is to the right and up, or positive. T2 is to the right and down, negative. So we get this. The goal is to find T2. So T1y is 25,601. X1 is 2. 2 plus 1. So T2 is 17,067 newtons. So just as in part 1, if I said, given this frequency, what's the tension in the string, you could figure it out. If I said, given the tension in the string, give me the tension on that end, you could figure that out. What I'm doing is I'm stitching them together like a big quilt. As with many things in physics, problem solving is taking a look at a problem and going, whoo, that looks bad. Are there parts of the problem that I can figure out that are small, that are manageable? And so what you do is you start poking it with a stick and pulling it apart. Now, I have a mass sitting in water. I know the tension up is 17,067 newtons. I know that there is a force down, force of gravity, which is mass times gravity, and this is the mass of the hanging object. And I know, because it's sitting in water, that there is a buoyant force pushing up. So if I said, given a string of a tension 17,067, that the density of rebellium is 2,500 kilograms per cubic meter, and that the density of water is 1,000 kilograms per cubic meter. If I simply said this, given this, what's the volume hanging there? That's a legitimate problem. And some of you may be thinking, bottom line, is this going to be on the test or the final? Not the whole thing. I'm not cruel, but definitely the parts within it do help. And then another thing is, if you could sit here and understand how to work this particular problem, this beast of a problem, you should be able to handle anything on the test or the final. If you could just sit there and go back and forth, figure anything out, stuff like this will help you get ready for the exams. It's sitting there doing nothing. The sum of the forces vertically is equal to 0. Tension up, buoyant force up, force of gravity down. Well, the tension I know. The buoyant force is density of water, volume times gravity. That thing is submerged. So the volume of the whole thing is what we're looking for. Now, the mass of the object, I don't know. I didn't give it to you. There's a substitution. You use the Swiss Army knife of equations. Density is mass divided by volume. Therefore, density times volume is equal to mass. This M becomes density of rebellium, volume, and gravity. What I'm going to do is I'm going to factor out a V and a G. So 0 equals T VG rho water minus rho rebellium. I'm going to shift this over, minus VG rho W minus rho R equals T, or V is equal to T over negative G rho W minus rho R. And so that's the volume. T 17,067. G 10. 1,000 minus 2,500. So the denominator will eventually become positive, and the whole thing becomes, drum roll please, oh, this is nice. Well, it's not a perfect number. 1.14 cubic meters. And that's the answer. It's like that saying, what's the best way to eat an elephant? One bite at a time. So with a problem like this, you've got to take small steps. Now, this took, well, it wasn't that bad. It took 33 minutes, and it took 2, 3, 4 small sheets of paper. There are physics graduate students who write like these 8, 10-page essays, all an equation for one problem in this weird script that doesn't even have numbers. So what I'm doing with this is with, I believe in it's best to sweat in practice than bleed in combat. Better to do that. Because if you guys get ready for the hard ones, the really hard ones, and really understand it, then you'll be ready for the smaller ones on the test. And so it's not that bad. When you think about it in parts, it's 3 parts stitched together. So, does that make sense? See what pedagogy is? Awesome. So this particular problem I've done before, but there was a student in the last lecture that said, when you said you could make it harder, what did you mean by that? That's it. But the bottom line is, that won't be on the test, that won't be on the finals. That would be great. Here's your one problem. Do it. You've got 3 hours. There you go. But it's something when you sit there and you look at the individual steps, it makes sense. The last new material that we're going to talk about is Doppler shifting. So we're finishing up sound. Everybody has heard Doppler shifting. Everyone has heard, there was a perfect demonstration the other day. Walking from Lewis to Turner Center, I'm crossing Turner Center, there's a car passing in front of me. It was a convertible, the people were playing the radio loud, and it was perfectly normal, and then the moment they hit the accelerator and sped away, the sound of the radio sounded weird because the frequency of the song dropped enough that the music got a little off key. When you have a car, it's emitting sound, and as it's moving with the sound waves in one direction. In the other direction, it's moving away from if the car is moving to the right and it's emitting sound, it's moving with the waves going to the right and away from the waves moving to the left. So as it's moving, it emits a wave so that the waves on the left are effectively deposited further apart than the waves moving to the right. For a person standing here, they'll hear a higher pitch frequency. So if you've got a police car coming at you, you hear that woo 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 woo, and the moment it passes you, it goes woo 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 woo, like it'll drop. Everybody has heard that. So the person to the right of, or basically in front of a moving source, the frequency that he hears, which I will call f prime, well, I could write f prime towards, is greater than the frequency that's being emitted. This person would disagree with the person that's hearing this, because he will hear a lower frequency than this person. And just before I start locking in the nomenclature, I'm just going to say F towards and F away. You don't really need the F prime. The fact that there's a T or an A there makes the prime irrelevant or redundant. There are equations that you use to determine the frequency. For moving source, the frequency towards is F divided by 1 something V over Vs. And the frequency away is F over 1 something V over Vs. Now the V is the velocity. The velocity of the source. The Vs is the velocity of sound. Which in physics 213 is 350 meters per second. Now, one of the questions that I have for you is this. A lot of times, I can't remember what the right equation is for this. The one thing that I do know is if it's a moving source, this little hunk of equations is in the denominator. Is it plus? Which one uses a plus and which one uses a minus? In order for Ft to be bigger than F, what must the value in the denominator be? Less than 1. To get a number less than 1, do I use plus or minus? I use minus. So for the Doppler shifting where the source is moving towards you, you use a minus in the denominator. For this, Fa must be less than F, which means that the number in the denominator must be bigger than 1. So it's plus. So as an example, police car moving away. You hear 1500 hertz. The policeman in the car hear 1700 hertz. What is the velocity of the car? So you're hearing 1500 hertz, the policeman says he's hearing 1700. What's the velocity of the car? He's in the car, he's moving with it, he hears the source. You are the observer, you're the one hearing the sound come or go away from you. So you're using this equation. So you use that equation, and then the next thing you do Actually, the first thing I'm going to do, get a new sheet of paper, is I'm going to bring that up and that down. 1 plus V over Vs equals F over Fa. So V over Vs is F over Fa minus 1. Or V equals Vs F over Fa minus 1. So this becomes 350 F, frequency of the source, 1700, divided by 1500 minus 1. .7 meters per second. Now I don't care what it is in miles per hour or whatever. I don't even care if that's a sensible number. But that's how you would figure it out. Likewise, if you have a source fixed and it's emitting sound, if you're the end observer who's moving with it, if you were just standing there, you would hear the frequency of what's being emitted. But since you're moving towards the source, you're going to be crossing those sound waves more quickly than if you were just standing there. It's a lot like it really is a lot like surfing. The waves are coming in. If you paddle against the waves, you hit the waves more quickly than if you were just standing there doing nothing. Likewise, if you're a person moving away from the source, it would be as if you're swimming with the waves. The waves are still faster than you, but they cross less frequently. That lowering of the frequency is the lower of pitch, the lower of tone. So in this case, the frequency towards and the frequency away is this. For a moving observer, that bracket, those parentheses are in the numerator. There's a derivation for it, but we don't have, I mean, we're just 213 students. When I go to MSMS, we're going to derive this stuff. And we'll have all sorts of fun. If I go there. But for the moving source or moving observer towards and away, towards you're going to hear a higher pitched sound. So this has to be plus. And for the moving observer away, that has to be negative. So if we had an example of you are running at, I don't know what a running speed is in meters per second, 10 meters per second from a 1500 hertz source, what F do you hear? What is the frequency that you hear? So, moving observer away. So you use FA is equal to F 1 minus V over Vs. Source 1500. Velocity 10. Velocity of sound 350. And you hear 1457 hertz. And so that would be the answer for that. So most of the problems are like this. Given a velocity, give me the frequency that you hear. Given the frequency that you hear, give me the velocity. Stuff like that. The last problem of Physics 213 that is because of new material is this. Years ago, I was standing in a Biloxi casino with my girlfriend at the time. And she asked me, what's the importance of physics? Why learn it? Why understand it? And I told her the story of the roulette wheel while we were standing right at the roulette wheel. And the dealer, or croupier, I don't know, the dude in charge of the roulette wheel looked at me and realized I knew what I was talking about. If you go to Tunica or any of the modern casinos, you will notice that on a roulette wheel table, there is a barrier around the wheel. It's like a half-inch plexiglass, or half-inch thick plexiglass wall, roughly 2 feet high, and it's adjacent to the wheel. Also on the wheel, there are these little diamond nubs that the ball can bounce off of as it's dropping down from the edge of the wheel. Who's responsible for putting this in? Physicists. Back in the 1960s and 70s, a group of physicists who were like grad students at UC Santa Cruz, in that time of casinos, there was no wall. In that time of casinos, there were no these little nubs. Also, until they got done with the casinos, you were allowed to bet on where the roulette wheel fell as long as the wheel, or as long as the ball was in contact with the top of the roulette wheel. From the time he puts the ball down and starts spinning, you've got until, you could bet before he puts the ball in play, up through the time he puts the ball in play, right until the time that the ball drops. What these people did is they got a hold of a roulette wheel table and put it up, thanks for the interruption, put it up in the attic of their house adjacent to the campus, and they played roulette all summer long. And what they figured out is a roulette wheel handler, whatever they call it, gives a consistent initial velocity to the ball. If they can sit there and watch this dude, they can figure out what velocity at which he's putting the ball in play. Well, how do they know that the ball is in play at what velocity? Or at a specific velocity? If you put your ear up to the roulette wheel, you will hear this when he puts the ball in play and as it's moving around. It goes na 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 na. The high na is the ball coming at you. The lower na is the ball coming away. Na towards, na away. So if what they figured out with physics, you can figure out the initial velocity of the ball. But you don't know the velocity of the ball. You don't know initially what the frequency of the source is. But if I know As that ball is moving away, I hear a frequency going away. And as the ball is coming at me, I know the frequency that's coming towards. There is a subset of Doppler shift problems based on this solution I'm about to work right now. It's been on tests, it's definitely been in problem sets, and it's been on the final. You're trying to figure out the velocity of the ball. You only have the frequency towards you and the frequency away, but I specifically did not tell you the frequency of the ball. What do we know about situations when you say, but you didn't give us that, and my response is, it's a correctly constructed problem? You don't need it. It's a moving source. So what we do is we take the frequency towards and we divide by the frequency away. It could be away over towards or towards over away, it doesn't matter. Towards away, that's a mutant V. And that equals each other. And what you see here, what I'll do is I'll do the next step without any canceling. This was in the denominator of the denominator. It comes up to the numerator. This is in the denominator of the numerator. It comes down. And what you notice is the frequency of the ball cancels. In order to determine the velocity of the ball, if you have the frequency away and towards, you got everything that you need. Now, what they had is they figured out the velocity of sound in air. They had the temperature, pressure, they figured it all out. In our casino, we're gonna still use 350. But this is the steps that you gotta know when you get to the those roulette wheel type problems. You cross multiply. You distribute. You isolate your V terms. Yeah, that goes over. You factor out. You start multiplying it out. And you've got the velocity of the ball. So let's say for an instant, this number is going to be nonsensical, or it's not really going to be applicable. But let's say you heard 1800 hertz and 1600 hertz, the frequency towards and the frequency away. 350 towards 1800, away 1600. 1800 plus 1600. And this gives you 20.59 meters per second. So from all of this information, the frequency of the ball coming at you, the frequency of the ball moving away, you're able to determine the velocity of the ball. Now, why is the velocity of the ball important? Because the initial angular velocity of the ball is v, or v naught, effectively, divided by r. We have theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And omega equals omega naught plus alpha t. What they did was they realized that if they listened to the wheel, they could figure out the initial velocity. If they have the initial velocity, they've got omega naught. They had a regulation roulette wheel table in their attic. They figured out the friction on this ball with the roulette wheel table, so they were able to determine alpha. They had this roulette wheel table and they figured out the specific angular velocity at which the ball would drop. They know the decay of the ball, they know the initial angular velocity, they know the final angular velocity at which this thing's going to drop, which means they know the time at which the ball's going to drop and start dancing around on the wheel. Now, this is an oversimplification of what they really did, but it explains the core manners. If they know the time at which it's going to drop, they know the time at which it's going to fall. When I introduced this problem, or this equation here, I said there's only one time where theta naught is going to be non-zero. Now is the time. They would watch the handler and figure out where he put the ball, and now they know theta. If you know where he put the ball down, how long it's going to take for it to drop, you can figure out where the ball is going to end up. You will understand theta, the angle associates with a particular bend on the wheel. And that theta means only one thing. Dollar bill, yo. Now, one of the questions is, well, how did they get the sound? They just couldn't, they're not perfect pitch people. How could they figure out the frequencies of the sound? Well, what they did is, one of them had a fake cast on. He didn't have a broken arm, he just put it in a cast. And in his hand, he had a microphone. And that microphone, he would just kind of lean up to the roulette wheel table. He was just some per individual. And he put his arm up to the wheel, and the microphone would get the frequency. Now, also, this was back in the early 70s. What they ended up doing is, the dude with the microphone, he had a little computer in his shoe that he could interface with it with like code. And he would input a place of the ball, the drop on black too. But it would say, I think it's going to drop on this half of the roulette wheel table. Now, if you study roulette wheel tables, you can bet one side or the other or green, which is there are two slots of middle. So it's a bet where there's effectively a 52-48 advantage for the house. But if you've got your little microphone and computer, you can change those odds from 52 to 48 for the house to 60 to 40 for the bettors. Is this cheating? Yes, it is. And so when the shall we say the Cosa Nostra found out what these people were doing, they told the dude with the arm in the cast, if you want a real broken arm, come and stay, but we suggest that you leave. And so they left. And then those two, the three major defenses, went online. You couldn't make a bet after the ball was in play. So it eliminated the ability for you to calculate what's going on. They put the sound barrier up so no one with a broken arm and a microphone in the cast could walk up to the roulette wheel table and figure out the frequency. And the last thing they did, which is the jerk move, they put the little nubs on the wheel. When that ball drops, those nubs add a layer of what scientists call chaos, a certain level of randomness that you sit there and go, I have no idea where this thing's going to go. So with those three defenses, they have effectively eliminated that type of physics. And it was very interesting because I'm basically standing over the wheel talking to my girlfriend, pointing at all the different parts going on, and the dude's just looking at me like, I don't know if I should kick you out or not, because you're not, technically it's not cheating just to talk about it. So people ask, why is physics important? That is it. You can make money with it. So, all right. As a reminder, review session, test 3 review on Thursday, tutorial review session on Friday. On YouTube, tutorials from previous semesters for Thursday's problem set have been posted. That's it. See you later.